Okay, Algebra 2, Senior, Final Exam Review Questions. Answers revealed. So in this case, we're looking to change this radical form to an exponential form. And what we're given here is an opportunity to look at, first of all, the fact that this 7v under here, that's what stuff is happening to. Now I want to change that into an exponential form. So to change something from this radical form to an exponential form, I know that 7v is going to be my main concern. The question is, how do I change essentially a cubed or a square root to the third power? So there's an understood 2 out here, even though it's not written. And then we know that this thing is raised also to the third power. Well, the way I do that is I simply look at this and say, okay, I'm going to take my exponent, whatever it is, and I'm going to put it over my root. And in this case, my root, marker's getting a little squeaky here, sorry. In this case, my exponent is 3, my root is 2, and that is my exponential form. Number 2, we want to simplify this thing. Okay? First of all, I look at this and I see that I have this written incorrectly. This is supposed to be 3/2. Hopefully what you see on your paper is 3/2. Okay? This can be a calculator thing. You can grab your calculator and you can simply take 16 and raise it, open a parentheses, 3 divided by 2 power. So that's 16 caret 3 divided by 2 power, hit enter, and there you have 64. So there's not a lot to that one. Simply put it in the calculator. Vertical asymptotes. Okay, 2 ways you can do this. One way you can do this is simply setting the denominator equal to 0. So if I take negative 4x plus 16 and set it equal to 0, okay, I could start by factoring out a negative 4. That would leave me with x minus 4 inside the parentheses. Okay, I'm just dividing out negative 4 out of each part. So when I'm looking for solutions, I'm looking for what makes that part 0. Well, what makes that part 0 is a positive 4. And that would be a vertical asymptote. So a VA would be at positive 4. X equals 4. Now the other way I can do that, if you grab your calculator, you can also go to your y equals, and you may, from what we did in class, you may even be more comfortable doing this. As long as you use parentheses where needed, you can grab your calculator, and in your y equals, you can do your x minus 2, close the parentheses, divided by, open parentheses, negative 4x plus 16. And, whoops, close that parentheses. Alright? And now, if I go to my table, I'm looking for where my y value is an error. Because when I see a y value that's an error, that means I have that horizontal or that vertical dotted line that the graph cannot cross over, or there's a hole at. And in this case, if you go down on your table, you can see when the x value is 4, the y value is an error. So that's a different way where you can say my vertical asymptote is at x equals 4. 2 different possibilities there. It's up to you. Horizontal asymptotes. Now these are going to be a little easier because you can just look at what you're given to determine these. A couple different possibilities. Okay, we're looking at the lead exponent. Lead exponent. Squeakiness is a little annoying. Sorry about that. So the lead exponent in the numerator is 1. The lead exponent in the denominator is 1. So when these are the same, which is the case we have now, come on, pen. When these are the same, then we use their coefficients as a fraction. So I have a 2 over a 1, so my horizontal asymptote will be at y equals 2, which is just 2 over 1. Okay? The other two situations you may need to be aware of is if the numerator's exponent is greater than the denominator. Okay, if the numerator's exponent is greater than the denominator, then there are none or no horizontal asymptotes. On the other hand, if the numerator's lead exponent is less than the denominator's lead exponent, then we always use y equals 0. So three different possibilities. 1, 2, 3. If they're the same, we use their exponents, or I'm sorry, we use their coefficients. Okay, we use these. Okay, if the lead exponents are, the numerator is greater than the denominator, then there are going to be none. If the numerator is less than the denominator, then the y will equal 0 will be your horizontal asymptote. Okay, this problem, we're going to talk about this problem in class just because I want to go over a couple of extra examples. I don't want to spend a lot of time on it right now, though. Evaluate this logarithm. Well, one thing you can remember is that this is right now is an expression. But if I set this thing equal to x, if you think about how we rewrite logarithms into exponential form, what we do is we take this base and raise it to that power. So 3 raised to the x, and we set it equal to whatever this was. So you can kind of look at this now, and this kind of becomes, okay, 3 to what power is equal to 27? And the power would be 3, because 3 to the third power is equal to 27. Now you don't have to necessarily rewrite it like that. If you go back to where you started, if you can look at those two numbers and say, okay, log base 3 equals 27, 3 to what power gives me 27, that's an even quicker way if you can identify it that way. Find the reference angle of negative 495 degrees. Let me undo that. Let's just think of it this way. Okay, if I start on my positive x side, and I'm going negative degrees, this way is negative, clockwise is negative. I know that when I go all the way around once, that's 360 degrees. So if I kind of add that in order to kind of remove it from what I've already done, I'm left with a negative 135 still. So now when I go from here to here, that's another 90. So what do I have left? I still have another 45 degrees left to go. So I'm just going to finish this the rest of the way, another 45, draw this, and this reference angle becomes 45 degrees. The reference angle pretty much refers to the angle or the number of degrees you have past the axis. Okay, so the last axis that I crossed was right here. So by reference angle, the question is, how much further did I have to go? And in this case, it was 45 degrees. All right. Let's do a little conversion to radians. Okay. Always want to remember that if I'm going from degrees to radians, when I multiply, I want degrees in the denominator so I can have degrees cancel. Because I'm always converting with either pi over 180 or 180 over pi. So if I go ahead, I cancel out these degrees. I want to reduce basically 590 over 180. Okay. Well, I know that if I'll just put this over 1. I know that if both of these end in 0, I could divide each of them by 10, and that would make this 59 divided by 18. 59 is a prime number. That cannot be reduced. So I'm just left with 59 pi over 18. Now, in case you're not great with your reducing, if you grab your calculator, if needed in this situation, if you did 590 divided by 180 and hit enter, gives you that nasty decimal. Math, enter, enter, changes that back to 59/18 for you. But for this one, you shouldn't have to go to that extent. Okay, that should kind of jump out at you a little bit. Okay. Positive and negative coterminal angle. A positive, okay, just so you know for future reference, if you're dealing in degrees, then you're just going to be adding or subtracting 180 degrees. Not 180. What am I talking about? 360. Sorry. Obviously, 360 is one complete trip around. So 360 positive or negative is what you're going to be using. But when we're in radians, you have to think about the fact that one time around is 2 pi. Okay, when we're not in degrees. So if I take this and I add 2 pi, I have to do a little converting here to myself to figure out, okay, how, what is 2 pi with 12 as a denominator? Well, that would be 24 twelfths. Okay? So if I do negative 13 plus 24, that leaves me with 11 pi over 12. There's the positive one. If I do negative 13 pi over 12 and I subtract 2 pi, well, once again, 2 pi is the same thing as 24 pi over 12. So when I do negative 13 minus 24, that leaves me with negative 37 pi over 12. So there's my positive and my negative coterminal angles. Okay. Now, can you use the calculator with these as well? Sure you could. Leave out the pi, and if I want to do negative 13 twelfths, I would open a parentheses and do negative 13 divided by 12, close that, plus 2 whole pi's. Notice I'm not using pi in the calculator. I'm leaving it out, sort of treating it like a variable. I hit enter. There's my fraction. If I want to, or my decimal, if I want to change that to a fraction, I press math, enter, enter, and there's my 11/12, which you saw here, 11 pi over 12. Just make sure that you leave the pi out. Whoops. The same went for when I did negative 13 divided by 12 minus 2, enter. And then I do math, enter, enter to change back to a fraction. There's your negative 37 over 12. So if you kind of leave pi out of it, treat pi as a variable, do the fractional part, change it back to a fraction, your calculator can help you with that as well. Okay. Find the exact value of the trig function. Okay, exact value. Now this is stuff we've done more recently, so this should be pretty fresh for you. First of all, we know that cosine, CAH, and SOHCAHTOA, we're going to be using adjacent over hypotenuse. Okay, now we're on the unit circle here, so I'm going to draw a unit circle. We know that in the unit circle, this point here is the point 1, 0, so we know that every radius in the unit circle is a length of 1. We just got to figure out where this 23 pi over 6 is on the unit circle. What's that angle look like? Well, if you want to, you can convert to degrees. When I convert from radians to degrees, I want radians in the denominator, so as to eliminate them, I'll put 180 in the top. Pi's cancel. So I'm doing 23 times 180 divided by 6. 23 times 180 divided by 6. 690 degrees. So this is 690 degrees. If I'm more comfortable in degrees, then I'd rather just do it this way. Now, I know one time around the unit circle would be 360, so I'll subtract that off. That's going to leave me with 330 degrees. So I went one whole time around. Now I have 330 left to go. Up here is 90. Here's 180. Here's 270. So I need to go another 270. So another 60 degrees. Okay. And what's left here is 30 degrees. The reason I draw the 30 instead of the 60 is because I'm going to make my right triangle this way. Okay, so writing 60 down here doesn't do me a lot of good. Okay, that doesn't really help me. What I need is that 30 degree. Alright, so now we know on the unit circle this is definitely going to be a length of 1. And if you think about those right triangles that we've been doing over and over and over again, if this is 30, this is 1, I know the shortest side, the side across from the 30, is always the 1/2. So this is 1/2. And I know the middle length side is always radical 3 over 2. Also got to keep in mind that because this is going down, that this is negative. Alright, so now that we've got our triangle labeled, here's our angle, and we're thinking about this as far as cosine goes, so we're looking at adjacent over hypotenuse. Adjacent to my 30 is radical 3 over 2. Hypotenuse here is 1. And we know that any number divided by 1 is just itself. So the cosine of 23 pi over 6 is equal to radical 3 over 2. Okay, I'm going to pause this for a second and go grab a different stylus that's not so squeaky. Okay, I have a new stylus here. Hopefully this one won't be so squeaky. Okay, solve and check for extraneous solutions. We're on to part 2 here. So you're going to need to show your work on these so you can get any partial points on the test. First things first, factor. And I'm telling you, last time we tested over this, that was the biggest issue. People were not factoring first. There are 2 parts to this that can be factored. Here and here. Take out a greatest common factor. They're the same thing. I can factor out an n, and it leaves me with n minus 6. Over here I can factor out an n, and it leaves me with n minus 6. So I'm just going to kind of cross these out because I don't need them anymore. I wrote them in a different form. So as I go through to each part, I want to make sure that I essentially multiply through in the numerator to cancel out all the denominators. So I just look at the first fraction. I know that I'm going to have to multiply by n times n minus 6. And if I'm going to do it there, I have to do it everywhere, regardless of what's in these other fractions. And the reason I do that is because n cancels with n minus 6 cancels with n minus 6, and the fraction, the denominator, is gone. Now lucky for us, we get the same thing to happen here, here and here. And then the third part, the same thing happens. So now if you look through at your denominators, they are all the same. 1. Okay? So, go back to the first part of this. All that's left is n minus 2. The middle part, you still have 6 times n, so that's 6n. And then the last part is n minus 5. So let's continue and solve. I have like terms. A 1n plus a 6n is 7n's. Bring down the minus 2. N minus 5. Collect all your n's on one side, so I would subtract n. That leaves me with 6n minus 2 on the left. Negative 5 on the right. Add 2 to both sides. So I get 6n equals negative 3. Divide both sides by 6. And n equals negative 1/2. n equals negative 1/2. Now, checking for extraneous solutions essentially means you want to go back up and just make sure that negative 1/2 doesn't make any of the denominators 0. And that's not going to happen in any of these cases when you plug that in. Okay. Whoops. I feel like I missed one here from the review. Let me go ahead and add a slide here and add that one in. The next one is 21 equals 3 times radical x minus 7. Okay. Biggest thing that I saw previously on this is people thinking that they could subtract 3 from both sides. Well, that 3 is being multiplied by radical x minus 7, so I need to start by dividing it. 21 divided by 3 is 7. Now the radical is by itself. Now I am allowed to square both sides to get rid of the radical. 7 squared is 49. The square root and the squared cancel. I just have x minus 7, add 7 to both sides, and I get a final answer of 56. That's the value of x. That's going to make this true. You can always take this up here and check your answer. 56 minus 7 is 49. The square root of 49 is 7. 7 times 3 is 21. Okay. The formula that we used here, P times E raised to the RT. $900 investment. Investment, investment, investment. That's the key word here. For that reason, that $900 is your P. That's your principal. Okay? This 5.5%, that's your rate. Time is what we're looking for. And they say that how long, how many years until the money triples, that's going to be your amount at the end. Now 900 tripled, hopefully you know, is 2,700. The principal was 900. E raised to the RT. Now yeah, 5.5% is our rate. But if I want to change that to a decimal, I move it 2 to the left, drop in a 0. This is 0.055 times t. Now, anytime that we're asked to solve for a variable up in the exponent, that's where the natural log is going to help us. But the natural log is not going to help us until we have this e to the 0.055t by itself. We can't take the log, natural log, before we do that. So I'm going to divide both sides by 900. 2,700 divided by 900 is an even 3. Those cancel. And now I have e to the 0.055t. Now, before you're allowed to bring that exponent down, this is the point where we got to get that exponent down onto Earth so we can use it. That's what the natural log does for us. Both sides. So we have the natural log of 3 equals 0.055t times the natural log of e. Now the natural log of e is just 1. So really we just have the natural log of 3 equals 0.055t, because the natural log of e is just 1. So to finish this, I'm going to divide both sides by 0.055. Okay. And if you go to your calculator to do that, it says to round to the nearest tenth of a year. So I grab my calculator, I press natural log of 3, close parentheses, divided by 0.055, enter, and I get about 19.9, well, let's call it 20.0 years. T equals 20.0. Because it was 19.97, it rounds the 9 up to a 0, which needs to round the 20 up. or the 19 up to a 20. All right, a couple more here. Sketch the graph, state the domain, the range, and the horizontal asymptote. So I'm going to grab my calculator. I'm going to go to my y equals, clear it out, and I want to put in 3. I got to try to find a way to sneak this. Oh, I can put it up over here. So I have 3 times 2 caret x, and then I got to come back down to earth here for my -1. Don't put that -1 up there in the exponent. And I'm just going to go to my table. And here I see my table where it looks like all those, I see the graph too, it looks like all those y values are approaching -1. They're starting to get closer and closer and closer to -1, but they are not touching -1. So that leads me to believe right there, which is right in line with the -1 right here. That tells me right away that my horizontal asymptote is at y equals -1. That's what I'm approaching, but I'm not hitting. Okay? You're going to want to go to your table and pick exact points off of your table. So like the point 1502 to the right, 1 up 5, 0, 2, -1.5, -2 and a fourth, -1/4. So -1 and positive, -1 and positive 0.5. That's about right there. And then -2 and down here. And from here, all these are just going to get closer and closer to -1, but not cross it. So my domain, that's my x values from left to right. My domain is going to be from -infinity to +infinity because I go all the way to the left. And although I start going up and up and up, I'm not going to have a vertical asymptote. It's going to continue to the right as well. The range on the other hand, stops at -1 and goes up to infinity. Oh, and you know what? Let's see here. Okay, I'm going to grab my calculator again here. I'm going to go to my y equals, and I'm going to drop in, clear this. You know what? Probably the best idea. Well, let's do this. Let's do log of x minus 2, close it, and then +4. Oops, I didn't do +4. I just put a 4. That's not good. Let me go back to that. +4. Big difference. Oh. Struggling. Not 4 + 4, just +4. Delete. There we go. +4. That's what I'm searching for there. Okay. So here's my graph. If you look at your table, you'll see a whole bunch of errors. As you should, because the graph stopped. It didn't go any further below a certain number. And that number was at the point 34. Okay, stop scrolling down. Must hit it one too many times. Alright, so right here is where we see this thing stops, at the point 34. So when I go to my graph, I'm going to make sure to the right 3 and up 4, I plot this point right here. Now from there, you definitely want to do, your best of grabbing another point or two. So 4 and 4.3, 5 and 4.47. Let's see, to the right 4 and about 4.3, 5, 4.7. You know, you're going to have a tough time getting any more exact than that. The key here is that your domain, you got to see that as only going from 3. I'm sorry. Domains are your x's. That's going this way. So that's actually from 4 up to infinity. Your range, that's going this way, that starts at 3 and goes up to infinity. Okay. As far as vertical asymptotes, you look at your sorry, let's go back to the graph here. I'm trying to go back to the graph, but this thing won't let me. Okay. So your vertical asymptote is this thing going up and down, you know. In your table, you're looking for where your errors start. Okay, and that error starts as we approached 4. Okay, so let's call our vertical asymptote here. I'm not 4, 3. Not a very good dotted line, but that's going to be at x equals 3 because the last x values that we saw were at 3. Okay. This last slide, okay, you're exempt from this question because we did not get to this before you seniors took your final exam. So you don't need to worry about this question.